So while Dalton and Avogadro and another chap called Berzelius and another one called Cannizzaro were arguing about formulas and relative masses and various things that are really fun to read about, but we don't have time to talk about them. Other scientists were busy at work isolating different elements, investigating their properties. So by the 1850s, there was a lovely database of about 60 elements and various properties of those. And of course, I hope you remember from some point in your schooling that this led to the creation of the most foundational, fundamental part of chemistry, the periodic table. But that's the next movie. For this one, let's just spend a little bit of time talking about what we mean by different properties of different elements. And we'll start off with something called sodium, discovered by Sir Humphrey Davy in the early part of the 1800s. Again, he was a contemporary of John Dalton. Sodium is a metal. Now, metal is a word you've heard an awful lot, but you need to be sure you know what we mean by a metal. Metals are substances that are ductile. They can be drawn into wires. They're malleable. They can be beaten into shape. They conduct heat. They conduct electricity. And they're shiny. Okay, there are some substances that we'll talk about in the next video that are some of these things. If they're just some of them, they're not metals. A metal has to have all of those properties. Now, sodium is a metal that is a rather reactive metal. Indeed, it reacts with water violently to make hydrogen gas, as we can find at this particular little YouTube video. Floats on top of the water, reacts violently to give hydrogen, catches fire, is jolly good fun and an amusing thing to do. What a tasty little video. I won't bother with the slower playback. Sodium also reacts violently with chlorine to make a white solid.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas.
Guy is so American, isn't he? Gas.
The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
That slow-mo replay. There we are. Awesome, isn't it? Now, that white solid has the formula NaCl. In other words, one sodium atom to one chlorine atom. Now let's think of potassium. Another element. It's a metal, also discovered by Sir Humphrey Davy. He actually discovered it a year before he isolated sodium. It's rather important. Again, we're not going to dwell too much on the history here. This will be a topic of your second term in your first year, actually, the main group metals. But for years and years and years, people have found it very difficult to separate compounds of sodium from compounds of potassium. Very, very similar properties. So it was a hugely significant feat when Davy was able to separate out sodium from potassium and show that they were different metals. Again, potassium is a metal. It's ductile, malleable, conducts heat, conducts electricity. It is shiny. Potassium also reacts violently with water to make hydrogen gas, as shown on this YouTube channel.
Ready?
Yep.
A little more vigorous than the sodium was. By the way, that video, it's part of a set of videos. I don't talk about other departments too much, but the University of Nottingham Chemistry Department with Sir Martin Polyakov, who I know you've seen, is the guy with the massive frizzy white hair. Really amazing set of videos. I have great admiration for the way that they did those, put them together in a nice scientific fashion. So anytime you're bored, you want something fun to watch, eschew Marvel movies and go and watch the University of Nottingham Chemistry Department's periodics. Table videos. Anyway, so potassium kind of looks like sodium except more vigorous, doesn't it? Also reacts violently with chlorine to make a white solid, as shown on this YouTube video. Heating up a little bit just to help it along. Goes on, we're waiting, and there we go. Very much the same idea as, again, the sodium. And again, similarly to the sodium, the formula of the white solid that is made is KCl, 1 potassium to 1 chlorine. So Humphrey Davy actually discovered more stable elements than anybody else in history, and another one of his was calcium. Again, it is a metal, ductile, malleable, conducts heat, conducts electricity, and it is shiny. It reacts with water, but it reacts with water much more slowly than sodium and potassium do, although it still makes hydrogen gas. And hopefully this video here will show it in action. So first of all, see, no gloves, no tongs, thunk. So much less reactive, so the chemist is not afraid to hold it in their hands. The thunk showing it's more dense than water is. Sodium and potassium floated on water, thus they are less dense. Calcium falls to the bottom, and you can start to see a few little bubbles coming out there, but certainly nowhere near as exciting as sodium and potassium. Calcium also reacts with chlorine violently to make a white solid. I haven't got a video of that, but that white solid's formula, CaCl2. So notice calcium compared to sodium and potassium. They're metals. They all react with water to make hydrogen gas. Sodium and potassium really, really quickly, really vigorously. Calcium much more slowly. They all react with chlorine violently to make a white solid. However, with sodium and potassium, there's 1 sodium or 1 potassium to 1 chlorine. With calcium, 1 calcium to 2 chlorines. Finally, let's quickly mention sulfur. Sulfur was not discovered by Sir Humphrey Davy. It was actually known by the ancients. It is the brimstone of biblical fame. It is not a metal, thus it is a non-metal. It's not ductile, it's not malleable, it doesn't conduct heat, it doesn't conduct electricity. It's a dry, lumpy solid or a powder. It doesn't actually smell itself, but it very, very quickly puts a little bit of H2S in the air when you open up, so everyone thinks it's smelly. But it doesn't really react with water. It does react with chlorine, with heat, and that's shown at this YouTube. I'm not going to show you because it's boring, because it just makes a yucky liquid. And the formula, yucky liquid, is SCl2. So anyway, we've just quickly gone through some properties of 4 elements, and what I hope that you appreciate is that the first 2, sodium and potassium, very similar to each other. Calcium, close, did the same sort of things but not nearly as well, and ended up with different composition compounds at it, and then sulfur completely different. Anyway, starting about 1810, there were enough data out there of the elements for people to start trying to classify them and put them in some kind of order. The first really worthwhile one of these that was reported properly was a chap called Dobereiner, who noticed that there was a triad relationship between some of the elements. For example, calcium, strontium and barium all behave similarly to each other. Lithium, sodium and potassium, there's 2 of our ones there, behave similarly to each other. Sulfur, very different from those ones, as we pointed out, but behaves similarly to selenium and tellurium, 2 very stinky elements as well. And then chlorine, bromine and iodine, even though chlorine a gas, bromine a liquid and iodine a solid, all had very similar properties. Moreover, Dobereiner, when looking at the relative masses, noticed a significant issue, and that was that the average of the first and the third of these triads was about the average relative mass of the second. So, for example, average calcium and barium together, you get 88.7, strontium's 87.6, pretty close. Even better with the lithium, sodium, potassium, because when you average the mass of lithium and potassium, you get 23, which is exactly that of sodium. So definitely some kind of pattern, some kind of relationship there in this triad relationship. About 20 years later, John Newlands noticed even further. He said, well, let's think about that relative mass. And when you order the elements in order of their mass, then you see a repeating property every set of 7 elements. Now, he confusingly called this an octave. Octave makes you think of 8. He wasn't talking about 8. He was talking about that repeating property. Okay, when you have your music octaves, they repeat, the notes repeat every 8. Newlands said our periodic properties repeat also, although in this case every 7. It's actually rather sad. Newlands did this in the 1850s, published a paper that was ridiculed by the British Royal Society, and so he kind of went away in disgrace. And then, of course, 15 years later, as we will talk about on the next slide, Dmitri Mendeleev came up with exactly the same thing, reported it properly, gets all the credit for it. Really, Newlands should be known as the father of the periodic table, but he's not. We have to get over it. It is, in fact, Dmitri Mendeleev, who between 1869 and 1872 laid the foundation for the periodic table. Now, here was Mendeleev's. He first of all ordered all of the elements known at that time in order of their relative mass. And what he noticed when he did that was that you could split it into properties in groups in these columns. So here's hydrogen, the lightest one, and then you go lithium, then beryllium, then boron, then carbon, nitrogen, oxygen in order of mass. Then you come back down to sodium. The next one, sodium, behaves very much like lithium, and then magnesium behaves like beryllium, and then aluminium behaves like boron, silicon behaves like carbon, and so on. And keeping on doing these, and you can see our little triads, right? There's the lithium, sodium, potassium, have the similar properties. Calcium, strontium, barium have similar properties. Sulfur, selenium, tellurium have similar properties. Chlorine, bromine, and iodine have similar properties. And of course, if we look at the ones we looked at, there's sodium, potassium, there's calcium, there's sulfur. Sodium, potassium in the same group, similar properties. Calcium, different group, but close by, because they're close-ish properties. And there's old sulfur, very different, all the way over here. Okay, now this looks different from our periodic table because he's thrown in what I hope you might remember as the transition metals here, kind of stuck in with this group here. Really, if one wanted to continue it on, you'd ignore titanium through zinc here, although they do have similar properties, and as we'll see when we get into the electronic structure, you can really see where these come from, and move the arsenic, selenium, and bromine up there. Okay, the distinguishing things that Mendeleev particularly noted, some of the properties with water and so on, but also their relative composition with oxygen and hydrogen. Lithium, sodium, potassium, and hydrogen, and copper, and then silver, and then gold, ones that we don't normally associate with that first group, all have compounds with oxygen in which 2 are the atom to 1 of the oxygen. These here, 1 of the compounds to 1 oxygen. Here again, a little bit funny, 2 of the compounds atoms, like 2 aluminiums or borons, to 3 oxygens, and so on. And then up here, you started to make compounds with hydrogen as well. Carbon, silicon, titanium all have compounds with hydrogen, where it's 1 atom to 4 hydrogens. Nickel, phosphorus, vanadium, and so on all have 1 atom to 3 hydrogens. And so this is where his groups came from. Now, there were 2 very important, notable things associated with Mendeleev. The first, other than, of course, the periodic table, first was he was very humble. If you notice here, tellurium and iodine, he had to switch those in terms of their mass, but he said, well, that's because maybe we don't know the masses perfectly well. But then the other thing that he was able to do, and I'll illustrate this on the next slide with a different form of the periodic table, based on gaps in this, he was able to predict the existence of elements that had not yet been discovered, and indeed fairly shortly after in some cases were discovered. So if I draw out, here's the Mendeleev table that we just saw on the previous slide, and then here is the elements arranged virtually as we would in our current periodic table. I know it doesn't look exactly pretty with all the little blocks, but that's then put in where our current periodic table would be. And if we notice this hole here, okay, that comes right underneath aluminium, and in Mendeleev's table there's this missing element here first and then another missing element there, and Mendeleev called this Eka aluminium. Another one right next to it called Eka silicon, and you probably should have heard about this in maybe some kind of your education before now. No elements there, but there were holes there in the periodic table, and Mendeleev predicted the existence of these elements, not just predicting their existence, but predicted their properties based on what he saw otherwise. So for example, the relative mass of Eka aluminium that we now call gallium, he predicted 68, it's actually 69.7. He predicted the density was 6, it's actually 5.9. Low melting point, it is a low melting point, 30 degrees. There's the formula of the oxide. Same thing for Eka silicon that we now know as germanium. There's his predictions, here's the reality of it. Now again, you should have heard of Eka aluminium and Eka silicon previously, but he also predicted a whole bunch of other elements that fun to throw out. Eka boron there, that actually fills that gap, and here that we now know as scandium. There's Divi manganese. Divi means that it's 2 removed. So there was another one here that was Eka manganese. This is Divi manganese. Eka manganese, which is technetium, is actually radioactive and so much harder to isolate and wasn't isolated for a while. But Divi manganese is rhenium, and indeed the predicted properties of Divi manganese and those of rhenium very, very similar to each other. To wrap up this slide, I talked about how Newlands does not get the same credit as Mendeleev does. Another chap who does get a little bit of credit, a lot of times you'll hear Mendeleev discovered the periodic table, but Lothar Meyer came up with the same idea at the same kind of time, blah, 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 just didn't publish it properly and so forth. So we do need to mention him a little bit. Now, indeed, Meyer did the same thing as Newlands and the same thing as Mendeleev, and listed out the properties compared to the atomic masses and noticed that periodicity, that reproducing of the properties. But something else that he did that I thought was rather cute was he determined the density of all of the elements, and from the density determined the atomic volume and plotted the atomic volume against the mass. And this is a reproduction of his original graph, and you can see again there's a nice periodicity to that pattern. So it goes up and down and up and down and up and down and up and down. And indeed, if we plot it out as it would be today, you can see again that even this atomic volume against the mass had this reproducibility, this periodicity in it. So you can see that sodium up there at the top and potassium up there at the top here that are left out, and rubidium up at the top. And so this helium's a little bit of a weird one, but again you can see this periodicity going through, and this was what Meyer demonstrated. And what's really notable about it is he did it in 1870, so before we had any nice fancy equipment. He was able to do some calculations that showed this wonderful periodicity was not just confined to the properties of the elements. So anyway, our next video is the same as I give to the first year students, talking about the periodic table and how it's broken down, some things that you really need to be familiar with that we will continue to refer to as we go through the course.